Francis Aston, English physicist. He invented the mass spectrometer in 1919. With it, Aston was able to compare the masses of nuclides. In particular, he was able to show that the mass of a helium atom is less than the mass of 4 hydrogen atoms by about 0.5%, which, in terms of the equivalent energy, works out at 27 million electron volts. That's a prodigious amount of energy. Enough, for example, to have kept our sun shining for 5,000 million years and more, while its hydrogen fuel is converted into helium. So with Aston's results, nuclear fusion provided for the first time a reasonable explanation of the energy release in stars. Could it also provide an explanation of the relative abundances of the elements? Well, if fusion is the explanation, we have to think of the whole universe as a fusion reactor, starting with hydrogen and producing not only helium, but all the other elements in a sequence of reactions, one after the other. And hydrogen is, after all, the most abundant element. This column represents the relative abundance of hydrogen, goes right up into the studio lights. And 4 atoms of hydrogen go together to produce an atom of helium. Then after helium, the abundances of the other elements fall off very rapidly. In fact, when we get to atomic masses past oxygen, the individual abundances are really very small. This little column here represents all the 80 or so other elements. They're all here. Argon, neon, another noble gas, sulfur, silicon, iron with the highest binding energy of all, magnesium, needed to produce life. All those 80 or so elements together make up less than 1% of the abundance of hydrogen. And that's reasonable if it needs a series of fusions to produce these elements. But even so, I really find it remarkable that all the energy of all the stars over 10,000 million years or more has used so little of the fuel and produced so little ash. It only makes sense if each individual nuclear reaction releases this tremendous amount of energy. So really it does all fit together. Fusion is the best explanation.
Now hold on, Alan. There is a problem, as you jolly well know. The problem is this, that if you're going to get 2 hydrogen nuclei to fuse together, then they have to get in really close to each other. And that isn't easy. Here is a nucleus. Because it's positively charged, it's surrounded by an electric field which repels any other positively charged particle, another nucleus, for example. The strength of the field falls off with distance. We can get a better idea of the strength of this repulsion if we represent the situation in terms of a graph of potential energy. As a positive charge approaches the nucleus, it comes up against a potential energy barrier. The closer in it gets, the stronger the repulsion and the higher the barrier. Until, that is, a point is reached at which the strong nuclear force takes over and the particle is sucked into the well. Once in the well, fusion can take place. Obviously, this ball's got to have a certain amount of energy in order to be able to get up over this potential barrier and drop into the well. And, well, presumably the same thing will apply to a proton. In order for a proton to approach another proton representing this potential well, it's got to have a certain amount of energy in order to get up over the top. Trouble is that the theory of what happens in stars tells us that the height of that barrier and the sort of energies you expect this ball to have, well, it just isn't possible for the ball to get over there. And therefore, presumably, fusion shouldn't take place.
Sir Arthur Eddington in the 1920s was well aware of these objections from classical physics, but he wasn't put off. His comment was, we don't argue with the critic who says the stars are not hot enough for these processes. We simply tell him to go and find a hotter place. Well, quantum physics, which was being developed at that time, showed that there was no need for a hotter place. George Gamow, who was born in Russia but went to live and work all his life in the United States, realized that the quantum process called tunneling could get through this apparent impasse. Russ and I are going to show that tunneling arises from the wave-like characteristics of matter. And we're going to start, in fact, with radio waves and see how they behave, and then go on to show that they provide a very direct analogy with the behavior of matter. And I have a little radio transmitter. It transmits waves of 3 centimeters wavelength, 10 gigahertz. And we'll see, first of all, what happens when we bounce those waves off a sheet of metal.
And the way we're going to look after this is to use this detector here. I'll just switch it on. And I'm going to now go hunting around to try and find that beam. Obviously, I've gone too far, so I'll just bring it back to where it was. Okay, well, I think that's the maximum position. So what's happening is that the beam from the transmitter gets reflected off the metal plate and along this direction here.
Well, here's our transmitter again, and this time we've got 2 prisms. But we're just looking at the front prism, first of all. And they're hollow prisms. They're filled with oil, motor oil, thick and dark, but it's transparent to radio waves. And in fact, the radio waves are going to come in perpendicular to this face, so they go straight through it, and go through the oil. And at the inside face of this front prism, there'll be a special sort of reflection.
Yes, in fact, it's called total internal reflection. The beam bounces off that surface, comes out, and through this surface, also perpendicular, and along this direction, where we can detect it.
Okay, so there's the reflection, but now the intriguing thing is what happens when we push these 2 prisms even closer together. I'll give you a hand. Okay, now that reflected beam has clearly got much weaker, but the beam can't have disappeared. It must have gone somewhere.
Okay, I'll go looking for it. First of all, I'll get rid of that and switch on this second detector. Right, so that's very interesting, because what's happening now is that the beam is coming in, striking the surface once again, but instead of being reflected, it gets across the gap. And there's still a gap here, although it's very small, there's still a gap there. It gets across the gap and carries straight on its original direction and out through this face.
I'm not sure about that. Maybe that beam was there all the time. We weren't looking there before.
Well, we can always pull the prism back and see whether it goes.
Okay. Okay,
Right,
now I'm
that's
convinced.
very nice.
Right.
So what we find then is that with these radio waves, provided this gap is quite small, about the order of a wavelength or smaller than that, the waves are actually able to get through the gap. And that is a phenomenon known as tunneling.
Now, we've already said that matter, neutrons and protons and electrons, have wave-like characteristics. That was the idea of Louis de Broglie, and it was the beginning of quantum mechanics. But it was only an idea. He never put it into mathematical form. So we may well question how close the analogy is between matter waves and electromagnetic waves. Well, there are many tests, but maybe the best one is the double slit experiment.
Well, now you can see the transmitter is facing a double slit arrangement, where the slits are separated by a distance of about an order of a wavelength. And I'm going to rotate this detector around on an arm, and I want you to listen to what happens. So what we get then is a series of maxima interspersed with minima. And that is known as the diffraction pattern you get from a double slit arrangement. And so whenever you get that kind of pattern, it's an indication that the beam you're dealing with is made up of waves.
In the last few years, it's become possible to do exactly the same thing with neutrons. We can't do that experiment in the studio because it needs a nuclear reactor. But here are the results. Neutrons striking a pair of slits ruled just 0.6 of a micrometer apart. A perfect double-slit diffraction pattern. There's no doubt at all that Louis de Broglie's idea was right.
Not only neutrons show wave-like characteristics, but also protons and other nuclei. That presumably means that we weren't right in thinking in terms of that proton being a ball trying to get over a potential barrier. Perhaps we ought to be thinking more in terms of a wave tunneling through. Here, the wave representing a moving nucleus encounters the potential barrier of another nucleus. It tunnels through and ends up inside, so allowing fusion to take place.
But although de Broglie's ideas allow us to draw these very plausible pictures with some confidence, they tell us nothing at all about the rate of the tunneling process for particles. First calculation of the rate was made by Gamow using the first quantitative theory of quantum mechanics, that of Schrödinger in 1926. So, was this theory right? Did it give the right rate for reactions? 1932 was about the best year physics has ever had. It saw the discovery of the positron, of the neutron, and the identification of the deuteron. Perhaps the most important event in that year, certainly the one with the most far-reaching consequences, took place in the Cavendish Laboratory in Cambridge in England. It was in this laboratory in 1932 that the first controlled, man-made nuclear reactions were produced. The atmosphere was pioneering. Since this was all for the sake of pure science, no attempt was made to get large grants. Everybody was expected to make his own apparatus. There was to be no decadent extravagance here. Lord Rutherford saw to that. Lord Rutherford, who, using natural radioactivity, had discovered the minute size of the nucleus inside the atom. The climax of the year came with the work of E.T.S. Walton and John Cockcroft. They built an apparatus to accelerate protons under the highest voltage which they could produce. The apparatus contained some very simple components: two T-chests, a petrol pump, and a piece of sheet metal that looked remarkably like a dustbin. But this apparatus made controlled nuclear reactions possible for the first time. This is an exact reconstruction of the particle flight tube, which was at the heart of the apparatus which Cockcroft and Walton constructed. It used the largest vacuum-tight glass cylinders which could be obtained in England at that time. That's what fixed the scale of the whole apparatus. Of course, in the Cavendish Laboratory, this was surrounded by transformers and rectifiers and capacitors, all the things that were needed to produce the very high voltage. 700,000 volts. No higher, because that would discharge across the spark gap. Quite a spark. At the top of the column, they had to generate some protons, and that's easy enough. They simply had to ionize some hydrogen. And then those protons were accelerated down the column by the high voltage to strike a target inside a wooden box. And the wooden box was shielded with lead. Well, with old accumulator plates, to be exact. And inside the box crouched Dr. Cockcroft, who was completely segregated from Dr. Walton. You'll see why that's important in a minute.
The reaction they chose to look at was lithium-7 plus a proton. For the most part, a proton wave encountering the electric field of lithium-7 is repelled and just scattered. But sometimes the proton is able to tunnel through the barrier, and fusion takes place. A new nucleus is formed, beryllium-8, but in an excited state called beryllium-8 star. it decays to 2 alpha particles. That's to say, 2 helium-4 nuclei. In the experiment, a target containing lithium-7 is bombarded by a beam of protons. What they hoped would happen is that a proton, on combining with the lithium-7 nucleus, would create beryllium-8 star. This decays to 2 alpha particles traveling in opposite directions. On reaching screens, they ought to cause simultaneous scintillations. So that's what they were looking for.
2 simultaneous flashes of light. That's why it needed both Cockcroft and Walton to do this experiment. They sat just as Russ and I are sitting now, except that they were in total darkness.
Now let's take a look at the Cockcroft and Walton apparatus in more detail. You can see there the vertical brass tube down which the proton beam passes. It also contains the target, which is placed opposite that hole that you can see. And then to the right of that is one of the 2 observation screens, which were placed on a horizontal axis perpendicular to the proton beam.
Alpha particles from the target emerged through tiny micro windows at the bottom of the proton beam tube, and they struck zinc sulfide screens where they made little flashes of light, and those flashes of light were observed through the microscopes. Each observer depressed a key when he saw a flash. And that punched a hole in ticker tape. 2 holes opposite each other meant a coincident arrival of 2 alpha particles. But of course they knew that this is what they were trying to find, so it had been all too easy for some subconscious bias to have crept in. So they swamped the noise of the keys with an artificial noise. Well, I think cooped up in this box for hour after hour with the noise and the pumps, it really can't have been much fun trying to concentrate all the time on the... And the ticker tape carried news, as it should, good news for once. Nuclear tunneling had indeed taken place, and Cockcroft and Walton had become the world's first successful alchemists. They'd transmuted lithium into beryllium. But much more important than that, they'd measured a rate for that reaction. Not quite in agreement with the calculations of Gamow using Schrödinger's theory of quantum mechanics, but pretty close. Close enough, certainly, to begin to be able to understand the rate at which these nuclei could be produced in stars. And with that measurement, they'd also found precisely the energy of the 2 alphas which were produced, a value which agreed precisely with the measurements of Aston and with Einstein's equation for the exchange rate between energy and matter, E equals mc squared. Part of Cockcroft and Walton's original apparatus is on display here at the Science Museum in London. It's placed appropriately at the entrance to the Nuclear Power Gallery because it changed nuclear research. Before 1932, nuclear research had to depend on natural radioactive sources, and that meant mostly radium and polonium. Cockcroft and Walton opened the way to an unrestricted study of all nuclei at all energies. Their work set in train a new style in nuclear physics, and it led to the development of more and more powerful machines. They developed their original apparatus into a most impressive machine capable of over 1 million volts. That was enough to produce a wide range of fusion reactions. Another approach was to use a magnetic field to hold the particles in a spiral path. And inside this magnet in California, already in 1932, was just such an accelerator. This tiny machine, one of the first cyclotrons, could have done Cockcroft and Walton's experiment. But they didn't do it, and in the event it seems that George Gamow was in a particularly persuasive mood when he visited Cockcroft, and so the experiment was first achieved in England. Lord Rutherford was quick to see the implications of the new machines. In 1932, he said, "It seems clear that this new method of attack, so successfully begun by Cockcroft and Walton, will, in the course of the next decade, bring us much new information on the transmutation of the elements." Then went on to say, "And it will help us to understand the processes of the production and destruction of nuclei which must occur in hot stars, the beginning of nuclear astrophysics. Remember the forecast of Sir Arthur Eddington that no hotter place would be needed for making nuclei." It was indeed within a decade, as Rutherford had predicted, that a set of stellar nuclear reactions was worked out. This type of machine helped a lot. The Van de Graaff accelerator, now a workhorse for nuclear astrophysics because it has a voltage which is stable and which can easily be adjusted to the requirements of the experiment. From the hundreds of reactions which had been studied by the 1940s, Hans Bethe selected a set which we know now as the carbon cycle or the CNO cycle, and which we recognize as an important source of energy in upper main sequence stars. That work tied together the two fundamental aspects of the structure of stars, the temperature needed for thermal pressure to support the star and the energy generation needed to keep the star shining. Fusion reactions in stars can start with protons and deuterons left over from the Big Bang, and then follow in moves up and along this chessboard of the chart of the nuclides. A move one along for an extra neutron, a move one up for an extra proton, and then stage by stage, steadily moving up the chart. Every square on this chart can be reached by some sequence of nuclear reactions, indeed by many sequences. Which of those many sequences is the one which is important in stars? Well, in the 50s and 60s, a lot of astrophysicists were working on that problem. Bethe, Gamow, and Hoyle were competing with each other to find the right series of reactions for main sequence stars. And that's where our story continues, beyond the main sequence, with a daring prediction tested by skeptical experimentalists, found to be true, and now accepted as the crucial link to the final stages of stellar evolution, where even the most massive nuclei can be produced.